All right, looking at page 22, we're writing the equations of polynomial functions from their graphs. We talk about multiplicity here, the number of roots that exist at a particular x-intercept, and it can be 1, 2, or 3. All right. Generally, we're kind of just observing the appearance of the graph at given x-intercepts, and then from there we're assigning multiplicity based off what we see. All right, so that's probably the most challenging part of this. So once we get a handle on that, everything else becomes a whole lot easier. So when you're dealing with a multiplicity of 1, this graph, it appears to be a parabola, behaves like a line around each x-intercept, right? And the natural question would be, well, what do you mean by behaves like a line? And if I were to just look at this portion of the graph, right, ignoring everything else, and I had to call it something, what would I say it looked like? I'd say it looked more linear than any other part of the graph, right? Same idea for this side. Just kind of get it into frame here. It looks more like a line around that x-intercept. So this would have a root of -1 with multiplicity 1. Right? This one would have a root of +1 with a multiplicity also of 1. Now in this case, around this x-intercept, a root, now it's scaled to go by every 2 boxes is 1 unit. So the root would be 1, right? This is supposed to be a 2. The more I zoom in, the less it looks like a 2. But this graph behaves like a parabola around that x-intercept. It touches and turns around, right? This looks like a 1 squared now. Let me move that out of the way. So this one would have multiplicity of 2, right? In this graph, around this x-intercept, so the root is 1, it behaves like a cubic function, all right? So that's multiplicity of 3. All right, let me just give you a quick side example here. All right. So let's say we're looking at something that looks like this. Oops. We're kind of used to the oopses by now, but it's probably as good as it's going to get. All right. So at this location here, it's behaving like a line. So that's multiplicity of 1. Mult. Around here, it's behaving like a parabola. Turns around upon itself. So that's multiplicity of 2. Again, we're focusing only on the x-intercepts here. And here, it's behaving, or at least my drawing is trying to make it appear as if it's behaving like a cubic, so that's multiplicity of 3. All right. So we'll look at a couple of examples because we need to write the equation of a polynomial given the graph, right? And you know there are ways to handle this that involve technology, but the problem that you run into with that is that it's going to be sort of limited to what you're able to observe from the function, right? So basically, if you don't know what kind of graph it's supposed to be, like what the overall degree of the polynomial is going to be, the technology isn't going to help you very much. It becomes just kind of an exploration and trial and error. I'm going to throw in another page here because for whatever reason I didn't leave enough room to do these problems. So we'll look at A. At this location here, It's cutting right through. So when it cuts directly through it, it's a multiplicity of 1. So this is a root of -3 with multiplicity of 1. This one has a root of 2 with a multiplicity of 2. All right, we've also gotten into the habit, hopefully, of identifying other pieces of information, most notably the y-intercept. I have a coordinate y-intercept here is 0, 1. We're actually going to need that. But beyond that, we kind of have pretty much everything we need. Now, there is a formula that I don't think I included here, but to find the polynomial function, p of x is going to be equal to k, some coefficient k, times x minus r1, x minus r2, however many there are. Right? And that could involve double and triple roots, which is where multiplicity comes into play. All right, so for A, I'm going to say I have a p of x. Well, actually, before I even get that, I'm going to say my first root, r1, is equal to -3. My second root, r2, is equal to a positive 2. Account for the roots. P of x, there's only those two roots, so p of x is going to be equal to k times x minus -3, right? Because the minus is built into the formula. Then x minus 2, right? Now, in the case of the root of, well, we're calling it r1 is equal to -3, that had a multiplicity of 1. So I'm going to assign an exponent of 1, which means I'm not really assigning anything unique, right? It's kind of is what it is, all right? But here I have a multiplicity of 2, so this binomial is going to get a power of 2. So p of x is equal to k times x plus 3 times x minus 2 squared. So now we need to figure out what the k is. We know from the graph that a y-intercept is equal to 0, 0, positive 1. And the definition of a y-intercept is that f of 0 is equal to the y-intercept. And so f of 0 in this case is equal to 1. But we're using p. So p of 0 is equal to 1. So if I figure out p of 0, right, replacing every x with a 0, that should be equal to 1. So k times 0 plus 3 times 0 minus 2 squared is going to give you 1 equal to k times 3. Negative 2 squared is 4, so 12, jumping the gun there. 4 times 3 will give you a 12, so 12k is equal to 1, making k equal to 1/12. So my p of x is going to be 1/12 x plus 3 x minus 2 squared. All right. Now, before I distribute all this out, I'm going to have a look on the numworks. I took the liberty of already putting the function in. So 1/12 x plus 3 x minus 2 squared. Have a look at it. It's not going to look exactly the same. It'll have the same structure and shape. We're really just looking for the important points. I have an x-intercept at -3, just like in the printed graph. My y-intercept at 0, 1. And my x-intercept at 2. And the multiplicities look right. It looks like it goes directly through at 3. All right. At 2, it looks like it's a touch and turn around kind of situation. Right. The only thing that people tend to kind of get a little iffy about would be the multiplicity of 3. If it goes directly through, even if it's not pretty, what did I just say? Then it's going to be a multiplicity of 1. It's only when it kind of bows into the x-intercept, right? And again, my drawing here wasn't picture perfect, but it should have been hopefully enough for you to say, well, it's not going directly through like a line would, right? So I probably could have drawn it a little bit better. I don't think there's any hope for me on this, but you know, something like that maybe. But that's the idea. It's got to go kind of curve into it and then curve out of it. If you're ever in a situation, and this isn't like an ironclad rule, but if you're ever in a situation where you're not sure if it's multiplicity of 1 or multiplicity of 3, and you have a pretty solid handle on what it's supposed to look like, then it's probably multiplicity of 1. Because if you have to sort of imagine that there's a curve there, then there really isn't, right? It's not always ideal where it's like, oh, it looks like a line going through. Sometimes it's a little iffy, like you see. Where are we? A couple pages down the line. I'd even say that this one is pretty straightforward, that it's a cubic, whereas this one is pretty straightforward that it's a linear. All right, so hopefully it doesn't end up being too much of an issue, but the idea is that you could recognize the different multiplicities. All right, now that we've sort of confirmed the graph, and if you're really not convinced, you can kind of zoom in and out. Let me just kind of get a better window here. I'm pretty convinced that this is the same graph. All right, once that happens, go ahead and distribute it all out. So x squared minus 4x plus 4. I distributed the easiest parts out first. Save the coefficient for last unless you love fractions. All right, so x to the third minus 4x squared plus 4x. All right, so plus 3x squared minus 12x plus 12. Simplify. 1/12. I got my x to the third. These two can go together. So minus x squared. These two can go together. So minus 8x plus 12. So 1/12 x to the third minus 1/12 x squared minus 8 over 12. All right, so we want to simplify that. So top and bottom is divisible by 4, so 2/3 plus, not 12, plus 1. All right, so that's my p of x. Notice how I have my equal signs every step of the way to establish that p of x is equal to each one of these things. All right, so it shows a progression along the way. All right, that's the notation part that I've been emphasizing throughout the entire course, and some of us have experienced losing some credit on assessments for not having that, and it doesn't make you feel good, but that if you know that's what the expectation is, make sure that you're adhering to that, please. I am going to double check. And the way I'm going to double check is by typing in my new function, all right, which should be equivalent to the one that's already there. So I got 1/12 x to the third minus 1/12 x to the second minus 2 over 3 x plus 1. Lock it in, go to graph. I'm only seeing one graph on the screen. I'll put it to auto. On auto, it should have, remember the key attributes of a graph would be the intercepts, turning points, right? So if you only see one graph, that means that they're occupying the same location, right? So if you're on the graph screen and hit the up and down arrow, you'll see it's going back and forth between blue and red. That's telling me that the blue graph and the red graph are occupying the same location. And And since my graphs are coded in red and blue, it's referring to these two graphs, and therefore they are equivalent, or at least graphically they are. All right. So I'll leave B for you to try. All right, so try this one. The key will be up in the completed notes. I already started talking about a problem, I think on page 24, so I'm just going to jump down to that. We're going to skip page 23 because this is stuff that we've kind of hit on pretty repeatedly throughout the unit. So if you'd like extra practice with certain polynomial function concepts, this is where you would go, but I'm not going to make this mandatory. I'll also ask you to try, this is probably the simplest looking graph, but there's a little extra going on with this one, but I'll ask you to try this, this problem also. The one little hint on this that I can give you is that you need another point in order to come up with the value of k, right? Because it has an x-intercept, that's the same as the y-intercept. So you wouldn't easily be able to figure out what the value of k is. But if you can estimate what, and this is really just to determine shape, if you could estimate the value of a point along the graph, like for example, I'll give you this one. If I go up here and go over, I know it's not the best looking graph in the world, but that's telling me that there is a point on the graph here of negative 1, 1. All right. And so what that would mean notation wise is that p of negative 1 is equal to 1. So you should be able to use that to figure out what the value of k is. But I'll let you try that first because I don't want to deprive you of the experience. All right. But looking at 12a, again, write the equation of the polynomial. I'm going to pull my roots. So I got a root. I'll just use the R1, R2, R3 notation now. All right, so R1, doesn't matter which one you call which, by the way, is negative 3, and this has multiplicity of 1. This has a touch and turn around kind of look to it. So my second root is negative 1 with multiplicity of 2. And my third root is 2 with multiplicity of 3, and I have a y-intercept of 0, negative 2. All right. So in my setup, p of x is going to be equal to k times x plus 3 minus the negative with a multiplicity of 1, so power of 1. Then x plus 1, x minus negative 1, x plus 1 with a multiplicity of 2, so power of 2. And then x minus 2, so x minus the R3, so x minus 2, raised to the power of 3 because the multiplicity is equal to 3. All right. I know my y-intercept is 0, negative 2, so p of 0 is equal to negative 2, which is equal to all of this. Except I'm going to swap out my x's. Oops, not too much. And replace them with 0. So in this next problem here, that p of negative 1 is equal to 1, you'll replace all your x's with a negative 1 instead of a 0. So negative 2 is equal to k times 3 times 1 times negative 8. So k is equal, well, we'll get to that in a second. 3 times negative 8 is negative 24. K, divide both sides by negative 24. K is going to be equal to 1/12. I promise they won't always be 1/12. I'm going to just kind of modify this one. X plus 1. X minus 2 to the third. this is the next one is going to be substantially different, so I'll get rid of that. All right, so this is what I'm looking at in terms of my intercepts. I have a -3, just like I have in this graph, a -1, y-intercept 0, -2, and x-intercept of 2. So I'm comfortable that I just found the appropriate k value. So p of x, 1/12, x plus 3, x plus 1 squared, x minus 2 to the third. And then we distribute all of this out. All right, so feel free to try that on your own if you want to cut the video now, or if you want to move on to the other problems and just check it against your or check it against the answer key. But at this point, I'm just going to carry out the multiplication, and this is going to kind of lead us into the next thing that we learn about, which is binomial expansion with Pascal's triangle, because that kind of gets a little crazy when you have to raise a binomial up to really high powers. So using Pascal's triangle for that will be helpful. We touched on that in the last unit, but we'll hit on it a little bit more moving forward. You could also try problem C and D. All right, so I'll put try. All right, and again, answer key will be posted for you. But like I said, I'll just do the distributor property on this. Pick your battles here. I tend to go for the most complicated part first, leaving that coefficient for the very end. So here it's going to be x minus 2 times x minus 2, x minus 2, x squared minus 4x plus 4, x minus 2. Each term gets distributed. So x to the third minus 2x squared minus 4x squared plus 8x plus 4x minus 8. Combining the like terms. This I can distribute. Again, x plus 1, account for the powers. X squared plus 2x plus 1. And we're going to distribute each term. I'll use a highlighter this time. So x to the fifth minus 6x to the fourth plus 12x to the third minus 8x squared. Plus 2x to the fourth minus 12x to the third plus 24x squared minus 16x. And you could layer it if you want, stack it one part over the other. Because what some people will do is they'll just kind of match up the different parts. You could write it like that so you can see what parts coincide. I mean, that's maybe I'll just do it that way. I already started doing it this way. So then plus x to the third minus 6x squared plus 12x minus 8. So I have my x to the fifth. I have a couple of terms that have x to the fourth in it. So that's going to be negative 4x to the fourth. Then I have a couple of terms that have power of 3. So that zeroes out. Then I have a couple of terms that have power of 2. Actually, it does, those two zero out. I just noticed that we do have an x to the third over here. So plus x to the third. All right, power of 2, 16x squared, 10x squared. Minus 4x minus 8. Now we just have to multiply that by x plus 3. So x to the 6th minus 4x to the 5th, x to the 4th, 10x to the 3rd, minus 4x squared minus 8x. Then run through with the 3. This time I'll stack it. So plus 3x to the 5th minus 12x to the 4th plus 3x to the 3rd plus 30x squared minus 12x minus 24. So x to the 6th minus x to the 5th minus 11x to the 4th plus 13x to the 3rd, 26x squared minus 20x minus 24, all multiplied by 1 over 12. So 1/12 x to the 6th minus 1/12 x to the 5th minus 11 over 12 x to the 4th plus 13 over 12 x to the 3rd plus 26 over 12, which would be 13 over 6 x to the 2nd minus 20 over 12, which would be 10 over 6, 5 over 3, x minus 2. All right, so we'll type all that in and maybe hold my breath. We'll see. A lot of room for mistakes here, so a little nervous, but if there is a mistake, then we go back and we find it. We make the adjustment. Hopefully it's not anything too catastrophic. Just be careful how you type it in, because I've made a mistake or two in my day where the math was all right. It's just how I typed it in the calculator that was the problem. So I'll give it a second look here. All right. Look at that. First try. And that's our complete solution. All right, so give those other problems a shot. Like I said, on page 22B, you could skip 23, so 24B, and then 25 C and D. All right. You don't have to do them all, but give them a good shot and check against the key.